Welcome to Study Loop.
So we're asked to work out how much heat is transferred into or out of a third of a mole of helium gas that takes the path ABC, shown by this pressure volume curve here. So looking at the first law of thermodynamics that's written out here, we've got the heat Q is equal to the internal energy change delta U, plus the work done by the gas W. So to work out the heat Q, we need to work out delta U and W. So starting out with working out W, we know that the work done by the gas is going to be equal to the area under this PV curve. So the area W, excuse my terrible handwriting there, will be equal to the area of this triangle plus the area of the rectangle below it. And as we know, the area of the triangle will be half times its base, which will be from A to C, so that's 0.008 meters cubed, times by its height, which is between 1 times 10 to the 5 to around 3.5 times 10 to the 5, so we will call that 2.5 times 10 to the 5 pascals. And that will be added to the area of the rectangle, which is just the base times the height, which will be equal to its base, which is 0.008 pascals, times by its height, which is 10 to the 5 pascals. Sorry, it's 0.008 meters cubed. That's why you remember your units. So that will be equal to around 1,000, if you put it into a calculator, it'll be equal to 1,800 joules. So we have our value for the work done W, so let's simply underline that there. So now we need to work out the change in internal energy delta U. So it's given that delta U is equal to the number of moles N times by the heat capacity at constant volume, which we will call CV, times by the change in temperature, delta T. Well, we can rewrite this using an expression for T in the ideal gas law. So that will be N multiplied by CV. And rearranging the ideal gas law, we can substitute for delta T. So it's P delta V, and then it will be taking the nr to the other side of that equation, which will be over nr. Now, the reason that we have a delta V here is because between states A and C, which I've marked here, delta V changes, as you can see by this V axis, and the pressure is just constant because it stays at this value of 1 times 10 to the 5. So that's why we have a delta V here and a constant P there. So now the only other value that we don't know is this heat capacity CV. However, for an ideal monatomic gas, we can say that CV is equal to 3R over 2, where R is the ideal gas constant. So subbing all of that in, using this new information, we can say that delta U is equal to 3P delta V over 2, as the N and the R will just cancel in this equation once we sub in CV. So plugging in some values to that, we have delta U is equal to, well, 3 times by the constant pressure, which we've established is 10 to the 5, multiplied by the change in volume between the start and end, which will be, well, 0.01 minus 0.002, so 0.008. That is a terrible 8. Over 2. And that comes out as 1200 joules. And I will just denote that in blue. So going back to our equation from the first law of thermodynamics here, all we simply want to do now is add the two results. So the heat Q will be equal to our work done, which is 1800 joules. Add our change in internal energy in the system, which is 1200 joules, coming to our final answer of 3000 joules, or 3 kilojoules. So this part of the question asks us to determine the value of Q for just the simple state A to state C without this intermediate state change to B. So due to energy conservation, our delta U will be the same as it was before, which we worked out as 1200 joules. However, we're doing less work. We're going straight from A to C rather than this intermediate step of state B. So we're only going by this dotted line here given on the graph. So the work done, again, is the area under the curve. So it will just simply be the area under this dotted line, which will be the area of this rectangle. So the area of the rectangle here. So that will be given by the length times the height. So the length is 0.008 meters cubed times by the height, which is 10 to the 5 pascals. And that comes out as 800 joules. And again, going back to our first law equation, we have the work done, and we also have the change in internal energy, so we just simply need to add them together. So Q is equal to 2000 joules. And as expected, this is less than if we were just simply to go from state A to state B to state C instead of just from state A to state C. And that's because we are doing less work by skipping this step here.